In this video, we're going to answer the following question. Why is the limit of sine of x over x is different from the limit of sine of x over the limit of x as x goes to 0? Okay, so basically what we know is that if we have two functions, okay, f and g, okay, with the limit of f of x as x goes to 0, in this case we can say the limit as x goes to a in general, but let's focus on 0. The limit of g of x as x goes to 0 both exist. Okay, so when we talk about the limit of f of x over g of x as x goes to 0, okay, and this is equal to the limit of f of x over the limit of g of x as x goes to 0, okay, but with one condition, is that the limit of g of x must be different from 0. Okay, here it's not satisfied. So when we take the limit, when we want to do this rule here, okay, so we have the limit of f of x as x goes to 0, 0 over the limit of g of x, which is x, it's 0. So we have 0 over 0. Okay? Therefore, we can't apply that one. And the main reason that we can't apply this rule here is that we have this one, this condition. So this is the condition that's preventing us from applying this rule here. Okay, but in any case, so the limit of sine of x over x as x goes to 0, okay, so when we try to evaluate, we're gonna get 0 over 0. Okay, so in general, when we have this limit, this is a warning, this is a sign that's telling us, hey, do some effort. The limit might exist, do some effort. I can tell you, you have to do some effort. You have to either rewrite the functions or do some effort, okay? But for us, we can use many techniques. One of the easiest one is that we can do a simple graphing of the functions, okay? So we know that the graph of the function, okay, y of x is equals x, okay, so it's this one. So the sign is almost the identical. Try to graph it using some calculator, okay, they will look the same, but remember that the sign of x is always less than x for at least x positive, okay, for the positive value of x. So once we do this, and we are not, when we get close to 0, okay, these two, they become the same, and therefore the ratio is 1. So here, okay, so this is an intuitive idea that's saying us that this limit is 1. Moreover, we know that so let's say f, the derivative of f at some x is the limit of f of x plus h minus f of x as over h as x goes to 0. Okay, so in as h goes to 0. So sorry, in this case we can take f prime at 0, okay, and we can take f of x as sine of x. Okay, so the derivative of the sine is the cosine, and it's 1. And when we do evaluate this one, we're gonna have, so here we're gonna have so at 0 we're gonna have this, oh, I want to change the symbols, so it's gonna be the limit of sine of h over h as h goes to 0, or I can switch, no matter, it's since h is a silent variable, okay, let's use x, but I don't want to use x because I used it here differently. So this limit is 1, so this is coming from the derivative, the notion of the derivative. There are other techniques. We can use geometry. Okay, so when we get 0 over 0 here, this is the key that we need. When we get 0 over 0, it doesn't mean that this limit doesn't exist. It does exist, and it's equal to 1. Okay, so when we do the ratio, we have one key. We need to make sure that this one must be different from 0. Okay, but in our case, this is 0. That's why we don't apply this rule here. We use other techniques. Okay, but we can use it anyways using L'Hopital's rule. But that one assumes the derivatives, and we are using the derivative. But anyways, so it's like circular definition. Some people complain about that, but the aim is just to explain the idea. Okay, we're gonna see more ways to compute this limit, but the key is that when we do this one here, we have to make sure that this is different from 0. Okay, if we get 0 over 0, that means we need to rework our function, use other techniques. This one, it's telling us, hey, I don't know, so do some work, do some extra work, or maybe try to find some other techniques. Okay, thank you.